So here's a quick video on the root test, which is the last test that we haven't talked about. So the root test is, as you see on your paper, basically you take a limit of the sequence as n approaches infinity with the nth root. You take the nth root of the sequence and then you take the limit of that as n approaches infinity. And based on what your answer is, just like the ratio test, if L is less than 1, then the limit then the series converges. If L is bigger than 1, the series diverges. And if L is equal to 1, the test fails and you've got to use some other test. So that's the idea. These are the root and the ratio are similar in that you really just take one limit, and once you get an answer, it tells you what happens, and you hope that it's either bigger than 1 or hope that it's not 1, because then the test fails. It doesn't do anything for you. So here's an example. So if we're going to apply the root test to this, we would say, okay, I'm going to use the root test, and that means I need to take the limit as n approaches infinity of 2 over n to the nth power absolute value. So that's that part there. And then we take the nth root of that. And you can see how this one is a natural for the nth root test, because when I take the nth root of something to the nth power, I end up with just 2 over n. Oh, whoops, I still have the limit. The limit as n approaches infinity of 2 over n. And of course, the limit as n approaches infinity of 2 over n, that is just 0. And since 0 is less than 1, we can say, therefore, this series, n running from 1 to infinity, of 2 over n to the n, converges. Because we met the requirement of the limit being less than 1. Okay, so now we have all the tests, and I will, like I said, I haven't made that video yet, but I'll make a video of me working through the worksheet, the practice sheets that have a bunch of different videos. I mean, a bunch of different infinite series. But I want to just sum up kind of what we know now. In general, if you're looking at a big pile of infinite series you're trying to test for convergence or divergence, I would suggest the first thing I always do, my number one task, is to do the Nth Term Test. And that, of course, remember, only tells you that it's divergent. You can never prove convergence with this. So it's divergent if the limit as n approaches infinity of a sub n is not 0. If the limit is 0, then this test fails. You have to do something else. But it's worth at least considering that every time you come to a series, because it's the one that we kind of forget about because it's so simple. But it's so simple, it's good to use when it works. Okay, so that would be my first step. My second step is to consider whether it's positive, whether the series is positive or alternating. If it's positive, then we have a lot of possibilities. We can, and usually my first thought is to consider the direct comparison. Oops. The direct comparison test, or the limit comparison test. And that really comes down to whether it looks like something we know. And usually we're trying to compare to a p-series or a geometric. Now I should back up and just say a moment, even before I consider the direct comparison, limit comparison, if it is a p-series or if it is a geometric or a sum of geometric or a p-series times a constant, then of course we can take care of it without any of those tests. But if it's not one of those obvious ones, then usually my first thought is, can I do a direct comparison or a limit comparison? And if neither one of those work, then my next step is to consider the ratio test, or the root test. And the root test or the ratio test is generally if I have factorials, powers, and exponentials mixed together. If it's just an exponential, then we're of course going to use geometric. If it's just a power, we could use p-series. But if it's a power and exponential mixed together, or definitely if it has factorials in it, then it's most likely going to require the ratio test. And the root test is generally we're looking for something that's kind of to this form, something raised to a power involving n. Okay? And then finally, A, B, C, D, E. The other option is the integral test. And that's usually, well, if it looks like it's an easy integral and you know the integral is, looks like it might be converging, that you might go to that right away. But usually it's hard to tell that just by looking at it. So it's often the integral test is kind of a last resort. If we've tried everything else and nothing else is working, then we go for the integral test. So those are your options with the positive. Then the other option, then the other case is if it's alternating, then you really have two options. Well, actually, if it's alternating, you can use the ratio test because of that absolute value. But which brings me down to the first option is absolute convergence. Absolute convergence. Usually if you can take the absolute, I mean, that's often again an easier step. If I can take the absolute value, if I can take the absolute value of it and it easily can show this converging, then that's a good way to do it, because if it converges with the absolute value around it, that means it converges without the absolute value around it. And then the second choice is the alternating series test. Alternating series test. And that's the one we use a lot for alternating series. So anyway, that's the rundown of this. Basically covers that sheet that you have. All the boxes have these sum up this list that I have here. But this, hopefully, the list gives you a better idea of kind of how to approach a problem. If you're looking at an infinite series just out of the blue, how do you decide what one to use? And this is kind of the progression that I would run through when trying to choose the test to use to prove convergence or divergence. All right. Have fun.